This is the chemistry of solid-state electronics. So first I want to start off by explaining what a diode is. A diode is an electronic component that prevents current from one direction and only allows it in the other direction or a forward bias. And to understand how they work, we need to know a bit about band theory. So in materials, materials at, we'll say, 0 degrees Kelvin, electrons sit at very low energy levels in what is called the valence band. And as you heat them up, they go through different discrete energy levels. And so at cooler temperatures, they will all be sitting in the valence band. But as you heat them up, they will jump into what is called the conduction band. And so for metals, the conduction band and the valence band actually overlap, which is why metals are able to conduct electricity. But for insulators, for stuff on the far right side of the periodic table, there's actually a gap in between the conduction and valence band. So at low temperatures, insulators do not allow electricity to flow. But if you heat up insulators and you get those electrons into the higher energy levels, they enter the conduction band. And this allows them to move through the insulator as if the insulator were a conductor. But for modern diodes, we look at semiconductors because they have a very small difference between the conduction band and the valence band. So one of the first diodes were the vacuum tube diodes. These consisted of a glass tube, and inside the glass tube, we had an outer anode and an inner cathode that would be heated up. And the reason that inner cathode needed to be heated up was to overcome the, I forget the term, was to overcome the work function of the material of that metal filament. And so as the work function was overcome, the electrons were freed from the surface of that filament and were able to flow through the vacuum inside that tube from the cathode to the anode. This is a process called thermionic emission. And basically, we give the electrons enough kinetic energy to where they can escape the surface of that material and flow through the vacuum as I described. These were invented in 1904, I believe. So they were the first diodes. But after vacuum tubes came, I skipped a slide. So the downside with vacuum tubes is that they were large, typically ranging from 1 inch to 6 inches, and they were slow, typically switching on the order of microseconds, and they were hot. They got up to 150 degrees Celsius while they were running, and they were quick to burn out. They only had lifespans of tens of thousands of hours, and they were energy hungry, requiring a rate of energy from 1 watt to 100 watts to operate. Compared to modern diodes are on the scale of nanometers. They switch on the order of nanoseconds. They do not get hot. They are not designed to run efficiently when they're hot. they can operate for hundreds of hours of operation hours, and they are not very energy hungry, requiring on the order of nanowatts, I do believe. So after vacuum tubes came the cat's whisker detector. And the way this worked is we had a metal wire that came into contact with a very small surface area to a semiconductor crystal. And what electrons had to overcome here was the difference in the work function between the metal wire and the silicone, or the semiconductor crystal. It was not silicone. I think it was a germanium lead alloy. After cat's whiskers came the doped diodes, which were made of doped semiconductors, typically metalloids. Metalloids are really good semiconductors, but really the only two we focus on are silicone and germanium. Silicone, I believe, is used for switching purposes, and germanium is used for light emitting purposes. So silicone is good because it's a semiconductor. And how doping works, we have a p-type material that we dope with group 13 elements, which gives the semiconductor extra holes. And holes are quasi-particles. They're not real particles, but we can think of them like real particles, and they are charge carriers. So electrons like to move between holes, and it actually increases the conductivity of that semiconductor. And it adds an extra energy level just above the valence band, in between, right in the middle of that band gap. And then the other kind of doping is N-type doping, where we introduce extra electrons into the material. And as we have an excess of electrons, that also gives a place for the electrons to travel, introducing more charge carriers and increasing the conductivity of the semiconductor. And what that does is it adds an extra energy level just below the conduction band. So we're minimizing that band gap, but there's still some level of energy input required to get the electrons to move across that band gap. So N-type semiconductors, as I stated, they are doped with group 15 elements, and P-type are doped with group 13 elements. And what this does is it creates what is called a p-n junction. When an N-type semiconductor comes into contact with a P-type semiconductor, the electrons from the N-type rush to fill the holes from the P-type, and the holes from the P-type rush to get electrons from the N-type, and they meet in the middle, and this fills the charge carriers. So essentially, this junction in the middle here becomes insulative because it has no charge carriers. What this also does, because the P-type is becoming, where it once was neutral, it's now losing its electron holes, so it's becoming negatively charged. And the N-type, where it once was neutral, is losing electrons, so it's becoming positively charged. And what this does is it creates an electric field pointing from the N-type to the P-type. So not only does the electric field have to be overcome, but we also have to supply it with charge carriers so that we can resolve this p-n junction here in the middle. For silicone, this takes about 0.7 volts, and for germanium, it takes about 0.3 volts. You can think about diodes as a chasm. So electrons will gather on one side, and some electrons will be able to cross that chasm, but very few will. Most of them just do not have the energy. And so by applying a voltage in the forward bias, it's kind of like we're putting a bridge across that chasm. And as that bridge gets closer to the other side, more electrons are able to pass until the bridge has made it all the way across and electrons can flow freely. Connecting a diode in reverse bias, here's a diagram. So as we apply a forward voltage, after a certain level, it becomes a short. But as we apply a reverse bias, it's like we're removing that bridge, and electrons start gathering on the other side. And when the electrons become so abundant, they will actually jump across in what is called an avalanche or a breakdown. And most diodes are designed to break before this happens. But there are a few exceptions, like Zener diodes, which their entire purpose is to run in reverse bias. The purposes of diodes: we've got rectification, voltage shunting, power conversion, and logic. So first, let's talk about rectification. If we put an alternating current into a diode, what's going to happen is that bottom is going to be cut off, and we are going to be left with just the positive voltage. We can take this one step further with this circuit here, which allows forward bias to flow through this diode and reverse bias to be stopped by this diode, and then forward bias in the opposite direction to be accepted by this diode and reverse voltage to be stopped by that diode. And what this does is it gives us an output voltage with a 100% work cycle rather than a 50% work cycle. So we are changing an alternating current with positive and negative voltages to just positive voltages. And if we are to add a capacitor across that load right here, it will turn that 100% work cycle voltage into direct current. So instead of getting a bunch of waves, we get a flat line and we get direct voltage made by alternating current. Another application is voltage multiplication. Essentially, this diode stops a negative voltage from getting to this capacitor, so this capacitor can charge, and then when the power supply goes in the opposite direction, this capacitor will discharge with the power supply and start filling this capacitor. And essentially, this just keeps happening until all the capacitors are filled. And for every capacitor and every diode, we get a new level of multiplication. So if we have a 10-volt input, it now becomes 20, and then 30, and then 40, and then 50. Now, the last and most important thing, especially in our day and age, is logic. Essentially, logic is what allows computers to work. Because of logic, we are able to have communications all over the world. Logic has completely revolutionized our world. And you don't need to know a lot about it other than by rearranging these, we can make complex circuits. And any one of these gates can be made using the NOR gate or the NAND gate. And we can make either one of those with diodes. But here's a diagram of how we can do that for the NOR gate. I'm not sure, I didn't go too into detail of how this works, but essentially, if A is on, then R will have no load or no voltage. If B is on, R will have no voltage. and if either of them are on, R will have no voltage. And by rearranging that in many different ways, we can get any one of those previous gates. Now, I'm going to talk about the different kinds of diodes. First up is the Zener diode. These are used to operate in reverse polarity. So as we have a reverse voltage, they will actually break down and become a short. And the reason this is important is that once their breakdown voltage is attained, they will maintain that voltage no matter what their input voltage was. So if it's designed for 10 volts and we put negative 20 volts in, we will get an output of negative 10 volts. And the reason this is important is because we can make power supplies, or we can add it to circuits where we do not want much fluctuation in our voltages. Essentially, how these work is that the P and N-type semiconductors are very heavily doped. The next kind of diode is the light-emitting diode. Essentially, we've got our diode here. We've got our P side on the left, and it is filled with holes. So that would be our valence band. The right side, the N-type, is filled with an excess of electrons. And when we power up our diode, we flood the N-type with excited electrons, and those excited electrons are going to drop into the holes. And while they drop, they are going to go from the conduction band into the valence band, and they are going to experience a difference in energy. That difference in energy is going to be released as a photon. Most diodes will release what is called a phonon, which is another quasi-particle that is a good way of thinking about heat. Another kind of light-emitting diode is an organic light-emitting diode. Basically, with these, the p-n junction takes place in an organic molecule. These are bigger, these are more flexible than LEDs, and we put them in TVs. Here is a diagram of their innards. This is trace aluminum. This is a kind of organic compound we put in OLEDs. I believe it emits a green light. Next is photodiodes. These are very similar to LEDs, except in reverse. So we've got our saturated diode. Our p-side holes are filled with electrons, and our inside is saturated with electrons. So as light hits those electrons in the holes, they become excited. And what they do with that excess energy is they jump from the valence band into the conduction band and lose that excess, or they don't lose the excess energy, they just use it to go into higher bands. And this creates a current through the diode. As I said, it's just like LEDs, but in reverse. You can actually use LEDs as a photodiode, but they're not very efficient. And you can use photodiodes as LEDs, but they're also not very efficient. So the difference between the two is that photodiodes are optimized to absorb light, and LEDs are optimized to emit light. Next up, we have tunnel diodes. I don't have much to say about these other than they are used for high-speed switching operations. We don't use them very much anymore, but they have a very thin p-n junction. So the electrons are actually able to quantum tunnel through the p-n junction and pass that barrier. So as we see, with just a little current before the activation voltage, with just a little voltage, we get a spike in current and then a decrease, and then it increases steadily from there after the activation. And as I said, these are very good for high-speed switching operations. The last diode I'd like to talk about is the laser diode. These are a kind of light-emitting diode, but the main difference between LEDs and laser diodes is LEDs will emit light in a broad area, and they don't always have a narrow, a discrete bandwidth that they emit. But laser diodes will emit a straight beam of coherent light, all of the same wavelength. And here is how they work. We have our saturated diode. We've got our N-type semiconductor and our P-type. And in the middle, we have a transparent, undoped semiconductor. The P-type has a polished edge, so it's kind of like a mirror. The N-type also has a polished edge. We've got a mirror at the bottom and a mirror at the top. That top mirror is important because it lets a very small amount of light pass through it. The charge carriers will meet in the middle and combine, and this is when it is not charged. And it's doped in such a way that this is a very thin axis of charge carriers. So as we apply a voltage to our diode, we get excited electrons, and those excited electrons will jump from the conduction band into the valence band and emit a photon, just like LEDs. Well, that photon is going to come back, and it is going to disturb an excited electron. That excited electron will fall into a hole and emit a new photon. These two photons are very important because they share the same wavelength, they share the same orientation, the same energy, and they travel in the same direction. They just do not share the same location in space. But other than location, these two photons are basically identical to each other. And so what happens is, now those two will go and they will excite more electrons, or bump into excited electrons, which will release more coherent photons. And this process is repeated over and over again. And we get a steady stream of coherent photons that are all basically identical to each other. And it's designed in such a way that the photons traveling along this axis will hit more filled charge carriers and release more coherent photons. And the result is that we get a beam of coherent photons leaving that diode, which we call a laser. Now, after diodes, we have transistors. Transistors are very similar to diodes, except they have an extra doped layer. We've got bipolar junction transistors and field effect transistors. Bipolar junction transistors look like this. They've got a p-doped side, two p-doped sides, and an n-doped interior, or two n-doped sides and a p-type interior. One side is called the base, one side is called the emitter, the other side is called the collector, and one side of the interior is called the base. We typically use these for amplification. So I will give you an example. When you speak into a microphone and it is broadcast out through a speaker, your voice oscillates a piezoelectric crystal. That crystal creates an alternating voltage in accordance to your voice. and that voltage will interact with the base here. And when the base is activated, it essentially creates a short between the emitter and the collector. So as you speak into the microphone and that electric signal that matches your voice interacts with the base, it changes the conductivity of the diode to match your voice. And we have a power supply connected to the emitter. So essentially, it's turning that DC voltage up here into your voice. And then your amplified voice will go into the speaker, and the speaker will convert that signal into sound waves. So you create a much louder version of your voice. Field effect transistors, or FETs, are very similar, except the base and the drain and source do not touch. They are separated by, I believe, an undoped substrate. And essentially what this does, that substrate is designed in such a way that it acts as a short between the two, or it can act to impede the two. So as we apply a voltage to the bottom substrate here, it creates an electric field which will either impede the current between these two, or it will aid the current between those two. However, I don't think aiding the current is very popular among field effect transistors. So from laser diodes to the amplification circuits inside of broadcasting towers, to the organic LEDs in your TV and the field effect transistors in your computer, the chemistry behind solid-state electronics has revolutionized our way of life and has even allowed us to land man on the moon. And with that, I would just like to thank all of you for coming and seeing my presentation. Do any of you have questions?
I don't really have questions, but I just have some comments.
Yes.
For one thing, I only teach the first 2 years of the electronics technology courses, so you went above my head about the third slide. But you have a you sound like you feel very comfortable and speaking, and that's a good thing. Also, another good quality that I like is that you think before you speak, and that's very evident as well. So I think you do a really good job of presenting material like you just did.
Thank you, Dr. McLean. I figured you'd have a better understanding. You do have your degree in chemical engineering.
Right. Yeah. I did a little bit. I took one course in circuits and one course in semiconductors. But that was a long time. But anyway, I just wanted to say you did a good job as far as the presentation. I like your slides.
Thank you, Dr. McLean. That means a lot to me. Does anybody else have any questions or comments?
Well, I'll tell you, Tyler, you have always been one of my favorites, no doubt in that, right? I have always appreciated you that way when you came as well. Very nice presentation, very good way of presenting. I really like it. And I'll just put one question to you. Okay?
Yes.
So when you are talking about the conduction band and the valence band, valence electron bands, right?
Yes.
What differences do we have in those in terms of metals, non-metals, and semiconductors?
Let's go back to the slide. You guys just sat through 70 slides. How do you feel? So, as we see with metals, Metals, at lower energies, all of the electrons will sit inside of the valence band. But with metals, the conduction band and the valence band actually overlap, which is why at low temperatures, metals are able to conduct electricity. For insulators, though, we actually have to excite those electrons with kinetic energy to get them into the conduction band, which is why why at higher temperatures, insulators will start to conduct electricity. And then semiconductors, they actually, I think they're very similar with insulators, that they start conducting at higher temperatures. They just have a smaller gap in between the conduction band and the valence band.
Yeah, semiconductors and insulators are the same thing. Semiconductors are a special type of insulator where the band gap is small.
Yes.
That's exactly how you think about it. And the big difference is what happens to the conductivity with temperature. What happens to the conductivity of a metal when you heat it? Does it go up or down?
It goes down.
Down, yeah. It's
And
already perfectly, it's already set up with the partially filled band.
I think
Can't make it any better conducted by giving it energy.
this is kind of a simplified diagram, but I think what we see with metals is that this top half here, this top half of the conduction band is actually missing, I think, for metals.
Well, it's just what happens at the higher temperature is you actually start to get the extra movement impeding the conductivity.
Oh, okay.
It's still essentially a partially filled band. It's already set up to be partially full. So the conductivity is already built in. You can't improve it by giving it more energy.
Hmm.
But semiconductors, insulators, that's where the conductivity increases with temperature.
Okay.
So you've got to have the electrons be able to be excited.
Does anybody else have any questions? Yes, Dr. Martin.
I might try the question on the LEDs.
Yes.
And you can probably say almost anything because I don't know the answer. But how do we, you showed a couple, I think, on the LEDs somewhere, right? How do we tune them to obtain different colors?
So it's all about the band gap.
This guy? Okay.
It's all about the band gap of the semiconductor. So actually, I forgot to mention this, but as the electrons drop from the conduction band into the valence band, that band gap is a difference in energy. So as they drop, they release energy equivalent to that band gap. And you can actually do the energy lost from the electron is equal to the energy of that gap, which is equal to the energy of the photon. And the energy of the photon is Planck's constant times the frequency of that photon. So by using different materials or different concentrations of doping will vary the size of the band gap and the output energy of that photon. So most LEDs are tuned in a way that that band gap will release photons with an energy level that we can see. So I don't have any numbers in my mind, but red light and stuff like that. And some are tuned to emit light that we can't see, like in TV remotes and stuff.
So I wonder then, I guess that would explain why white light is so hard.
Yes, white light is a mix of lights.
Yeah,
So
you have to do anything at all about that.
you need,
How do these guys produce the light?
for white light, you need at least 2 diodes. And for that, we'd have to look at a color diagram, actually, which I don't have on here. So We pick 2 or even 3 colors on here. So if we were to do, let's say, red, we would go opposite of red across this middle region here. And we would pick a color directly opposite. And by tuning the voltages we give to those LEDs will change the color of light we see. And for white light, it's tuned so that the photons emitted are in concentrations kind of equivalent, so we get white light. But for TVs, we have a red diode, a blue diode, and a green diode. And
That's diagram like that.
yes, and so by mixing these 3 types of photons, it tricks our brain into thinking we're seeing white light. Even here, we're only seeing 3 colors at any given time, but our brain mixes them together and we start thinking that we see yellow or magenta or cyan. But in reality, we are only seeing red and blue and green.
Those are the primary colors, right?
Yes. Do we have any more questions?
Yeah, you mentioned a phonon.
Yes.
But diodes, right?
Yes. Phonons are quasi-particles. So just like electron holes, they're not actual particles, but we can think of them like that. And a phonon is a quasi-particle of heat that I believe thermodynamic engineers will use to simulate heat in simulations.
That's about, essentially, as far as I'm aware of it, it's thinking of heat as a particle, just like we can think of light as a particle.
Okay.
And so phonon is a particle of thermal energy. When we have to have thermal energy also be discrete.
Right.
And then I'm done.
Yeah.
That's it. That's all I can do with phonons.
Yes. They're not a very interesting particle, in my opinion.
Those MCs where, you know, energy be converted to matter and both ends like undo what we do.
I was thinking that we're similar to like sound, but perhaps the electrical version, but you don't know.
No, phonons are just heat. They don't have to do with electricity.
Okay. Cool.
Dr. McLean?
So what led you to choose this particular topic?
Well, when I was in high school, I took a class at the university here called Solid State Electronics. And then this semester, I took a chemistry course on solid state. So I thought it would be easiest to make my presentation for the solid state chemistry class on solid state electronics.
And what have you learned about the research process?
So I actually learned quite a bit. I learned how light emitting diodes emit light. That was new to me. I learned the purpose of Zener diodes. I learned oh man, I learned so much. It's hard to really say.
Really what I'm asking is, what have you learned about doing research?
Oh, research is pretty difficult. A lot of reading, a lot of sorting through information that isn't really relevant to you in order to get to the information that is.
It's not just me.
Yes, it's also very interesting to uncover these little hidden gems of information that you find interesting.
But all that stuff, even if it wasn't relevant to what you were going to be speaking about, it's still things that are interesting to know.
Yes. I'll give you an example. When I was researching, I think it was N-type doping, I learned that they use N-type N-doped semiconductors in radiology, but I can't remember what for. I think it was neutron emission. They used them somehow for neutron emission, and I really thought that was unique, but it just didn't fit my presentation, so I didn't put it in there.
So what are your future plans? I'm assuming you're a senior this year.
No, I'm a junior. I have senior hours. I have over 100 hours, and I would be graduating if I stuck with my original degree plan, but I decided to give chemistry a try. So I'm a junior.
What was the original plan?
Well, I'm not really sure. I made it when I was in high school, but I was going to graduate here with a bachelor's in electronics technology, and it just didn't feel right for me, so I switched to chemistry. It was either going to be chemistry or computer science. Any other questions? All right. Well, thank you all for coming.